Let's do that later. Let's jump into databases in the microservices world. This is really, really fun. Today, we're going to talk about microservices, and in particular, how we do databases in that microservices world. Here's the part where I tell you I'm definitely going to post the slides on my site tonight. You'll go look on my site tonight, tomorrow, next week, next month. In about 3 months, you'll get tired of waiting. You'll email me. In about 6 months, I'll reply and say, no, I'm definitely going to post them on my site tonight. I've been the victim of that, and I don't like that at all, which is why you can go to robrich.org right now. You can click on presentations, and here's the slides that we're going to look at right now. So they are on the website, ready for you to look at right now. While you're there, click on About Me, and you'll see some of the some of the stuff that I've done recently. I'm a Microsoft MVP. I'm a friend of Redgate. AZ Give Camp is really fun. AZ Give Camp brings volunteer developers together with charities who otherwise couldn't afford software services. We start building software for them Friday after work. Sunday afternoon, we deliver that completed software back to the charities. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for the next AZ Give Camp. Or if you'd like a Give Camp in your area, hit me up on Twitter or by email, and let's get philanthropy installed in your area as well. Some of the other things that I've done, SQL Source Control Basics, that was a lot of fun. Mine is Chapter 8. I was on the Gulp team as a core contributor in version 2 and version 3. One of the things I'm particularly proud of is I replied to a .NET Rocks podcast episode. They read my comment on the air, and they sent me a mug. Woo! So there's my claim to fame, my coveted .NET Rocks mug. So let's dig into databases in the microservices world. Well, when we look at microservices, oh, we talked about this guy. When we look at microservices, we've kind of made this history transition in our industry. We started out with spaghetti. We moved to lasagna. And now we're kind of in the ravioli phase. I like this analogy because, we used to just kind of design everything together, and it was kind of messy. And then we went into lasagna where we had these tiers of things. And now we have ravioli. We have these little microservices that compose interesting things. So said differently, here's monoliths on the left, where we have all of the components of our application, and they're all compiled into one thing. And we'll deploy that one thing together because, well, deployment is hard, and we don't want to do hard things. So we take all of our pieces, maybe it's an N-tier application, or maybe it's a big ball of mud, and we'll deploy it at once infrequently. Now, on the upside, yeah, deployment was hard and we didn't do it very often. On the downside, that's one big thing that changes infrequently. So we chose instead to move away from that and move towards microservices. Yeah, Sean, I got mugged. So here in microservices, each one of these little pieces is a separate service, and it'll do a little task. And so now when we need to upgrade a particular service, we can upgrade only that service without having to upgrade the entire application. Part of what made this process easy is that deployment was no longer hard. We now have containers. So each of these could be a separate container, which is really cool. So now we have microservices, and as things move, a microservice may choose to call another microservice to get data from that particular service, or a microservice may need to, or a microservice may go to its data source to get data for that particular service. So microservices. Each microservice does one small job. It's easy to deploy with containers. We can scale each service independently of other services, and they're really easy to replace. If my microservice needs to evolve or needs to move to a different technology or solve a different business problem, I can replace that one microservice. And as long as I subscribe to all the other APIs interfaces correctly, I can replace that one service and upgrade my system in pieces, which is perfect. One of the core tenets of microservices, it owns its own data. And so microservices owning its own data is perfect because now I don't need to say, well, who's messing with this table? Can I evolve the schema? Well, when a microservice owns its own data, it knows exactly who owns the schema. That particular microservice owns the schema. So we saw here that each microservice has its own database. Well, that's really cool. But usually when we get to this point in the architecture, we do something like this instead, where we have lots of microservices and it's wonderfully broken out and it's distributed and we have all these pieces and we have a monolithic database. Well, why do we get here? Well, there's lots of reasons, but for the most part, the reason that we got here is the DBA said no. Well, why did the DBA say no? Well, the DBA said no because his job is to protect the infrastructure, to maintain uptime. And the way to keep uptime consistent is to change less. Well, maybe, probably more so. Provisioning the database is hard. And so if we have lots of little microservices and they each need, let's coin the term, micro-databases, well, now I'm spinning up a whole lot of databases. And the DBA is kind of like, I don't want to spin up databases. Spinning up databases is still hard. Containers make that easier, but it's also really easy to do that wrong. If we have too many little databases, there's two kind of big things that we need to remember to do. Have we backed up this database consistently? And have we secured the database? Do we have user authentication in place? And if we have lots of databases, it's really easy to accidentally get to the end of this process and go, oh, yeah, can we restore that database from last night's backup? Oh, we never backed up that database? Okay, yeah, we're pretty screwed. And so the DBA is pushing back because he doesn't want to set up another database. I get it. I get it, but I don't get it because, well, as we move towards microservices, we want to move also towards micro-databases. Well, if we must use a monolithic database, there's mechanisms to be able to handle that. Bounded context is really elegant. Bounded context creates the subset of this database that applies to a particular context. So for example, let's look at a shopping cart metaphor. If I have a shopping cart microservice, then it needs data about the products. It's going to own the product list. But it doesn't need to own the customer details. It just needs to own the product list. So we'll create a bounded context around the products, and we'll give that bounded context to the shopping cart. Well, kind of. Shopping cart also needs to be able to create orders. So we may have that order database, but more things need to own the order. So perhaps the shopping cart microservice calls the order creation microservice to actually do the thing. Or perhaps the shopping cart UI includes both the product catalog microservice and the order creation microservice. That might be an interesting mechanism. But in each of these cases, we've created that bounded context. We've created that small little circle around the data that we need to accomplish this task. And that bounded context then doesn't know anything about all of the other pieces of our application. That's perfect. We have lots of these little bounded contexts, and we can kind of pretend that our database isn't a monolith. Now, we're pretending, but it's a good way to pretend and kind of get used to this concept of micro-databases without having to re-architect our data storage mechanism. So in places where we must use a monolithic database, then bounded contexts are a good strategy. Well, how do we get to micro-databases? Well, what do we need to be able to pull this off? Well, in particular, these micro-databases, these little databases, are owned by the service that constructs them, but we also need all of those security procedures. We need the little pieces of, we need each little database to have backup and authentication. And so to get to micro-databases, we really need automation. A micro-database, we can define that as owned by one microservice. Other services will call this microservice to get at its data. And so we see that here where these microservices may call into other microservices to get at the microservices data. So microservice, some of the things that we struggle with now as we get to micro databases is, how do we do joins? How would we do a join across multiple bounded contexts? Because the bounded contexts don't know about each other. That's kind of intentional. A great solution here is a service bus. We could create a service bus like Kafka, and as the data changes in our microservice, we can publish that to a topic within Kafka. We could also do a similar thing with nService Bus or with BizTalk or anything like that. Creating this mechanism of streaming these events into the service bus is a great way to be able to publish changes. And then consuming things can now listen to the events that they care about and store that, that extra data. Now, perhaps they don't need all the data. Maybe they only need those small portions of that data that they'll want to join against. So we're denormalizing that data, but it's totally fine. We're denormalizing it so that we can make it more efficient for each little microservice to consume that separate data store and own their own schema. We'll call this event sourcing. Event sourcing is that mechanism of publishing events from one microservice and consuming them in another microservice. So we may have some microservices here whose sole job is to listen to the event source and publish new events, having transformed them in interesting ways. They may have no UI at all. That's kind of perfect. That's great. So micro-database. Let's talk through some examples of some interesting micro-databases. In a shopping cart, who owns the customer record? Who's responsible for that customer piece? Is it the shopping cart? The shopping cart is creating orders for customers, and so they have to verify that that customer is correct. Or should billing own the customer? Because they're going to store credit card information, and that's sensitive. We don't want to leak that across microservices. Or human resources? Should human resources own the customer record? Human resources has really sensitive stuff that they don't want to leak out. Or maybe sales, because that's the first time we see the customer. But sales has interesting validation requirements. To purchase an order for a customer, we need to have a valid address. But sales may get a lead or a prospect, and all they have is a name and a phone number. They don't have an address yet. So if sales was to own the customer record, then validation would be really inconsistent across the system. So who owns the customer record? Well, let's turn this on its head and say, what is a customer? Well, to sales, a customer is a name and a phone number. To human resources, a customer is an account number plus a whole lot of other information around that customer. To billing, a customer is a shipping account and an account balance, or a shipping address and account balance. To the shopping cart, a customer is recent orders. So really the central piece of that is the account number. And so I would propose we create a new microservice whose job it is to own the account number. It creates that primary customer ID and the account number, and maybe that's all. Maybe we put a name in there, but maybe not. Then shopping cart can have a foreign key off to that, either the account number or the customer ID, probably the customer ID. And the billing department can have a foreign key off to that customer ID. Human resources can create a foreign key off to that customer ID. And then in the human resources section, they can put all that sensitive data. Sales will never see that. It's not part of the customer record. It's part of the human resources customer profile. Now that's really cool. As we create these bounded contexts, these microservices around different parts of data, the customer microservice can own creating new customer IDs and own making the account number unique. And that's all it needs to do. Everything else then has foreign keys off to this customer microservice to be able to keep track of the other details that they need associated with this account. These, pardon me, these different microservices can have different pieces of information. They can extend the customer to identify the different details that they need. while having a foreign key back to that one central customer piece that owns pretty much nothing, only that account number. That's perfect. So now we have micro databases. We have the automation enough to be able to create these little databases, to enroll them in backup and user authentication. And then each micro database owns only that portion of data that that service needs. That's perfect. We may also have a bus going across them where we're publishing those events, and that can be really helpful as well. So what's interesting is, as we have all of these little databases, all the little databases don't need to be the same kind of database anymore. Now, the concept of a monolith database, they all did, but in micro databases, they don't. I love this quote. It was said by me right now. It's hard to hear the laughter across the audience. Hopefully that was a funny pun. Okay, so they don't all have to be the same type. That's really, really interesting. So now we can create each micro database and create it as the type that makes the most sense for that database. That's kind of perfect. So let's dig into different types of databases. And we'll look at each type. We'll look at the pros and cons of that type. We'll look at where it makes sense. And I'll give you some buzzwords about some examples of databases. Not that I'm promoting a database today, but that you can then use those Google terms to find more about the types. Relational, document, graph, key value, time series, search, object, file system, column store. And we'll dig into Nosql, which is really fun. Nosql is a cool thing that we'll start to discover. So here's the different types of databases that we'll look at. With each, we'll look at the characteristics of that database type, pros and cons, when it makes sense, and an example of each of those database types. So first up, SQL database or relational database. We can think of this like Excel spreadsheets. In an Excel spreadsheet, I can put data anywhere, and so it's not quite that. It's not a perfect analogy there, but let's create a spreadsheet, and let's assume that all of the data in each column is the same type. So if I have a column that is states, I'll only put states there. If I have a column that is prices, all of the values in that column will be a number. The cool thing about a SQL database is that I have consistent rows and columns. I know that a row is going to have data in each piece, and I know that each piece is the same type across all the rows. The SQL engine has been optimized for a real long time, so it's really good at processing these SQL queries and coming up with results in really elegant ways. For the most part, give or take, the SQL engines across database vendors are pretty much the same. They all do their own extensions to it, so it's not just plug and play. But SQL is more or less SQL across all the databases, and that's pretty cool. One of the things that's particularly cool about SQL databases is ACID compliance. ACID compliance, atomic, consistent, isolated, durable. I know that if I create a query against the database to update some data, either all of that data will get updated or none of it will. I know that by the time my database says that it's done and that data is committed, that data is committed. I'm not going to get half of it in and half of it out. As you grab these slides from robrich.org, you can click on each of these blue links to learn more about that piece. And these slides are up on robrich.org right now. So ACID compliance. By comparison, eventual consistency. I've seen some articles compare ACID and base, and I think that's pretty interesting as well. But the opposite of ACID compliance is eventual consistency. Eventually, I'll get the data up to date. We can think of this not that unlike walking into Starbucks. When I walk into Starbucks, they don't hand me the coffee cup and then come by and hand me some water and then come by and hand me some foam and eventually kind of build up my coffee cup. Rather, they give me a token. They take my name and they say, okay, when we're done, we'll give you a call back and we'll tell you that this is done. A similar mechanism is a bank statement. If I go charge something right now, it probably isn't on my bank statement yet. But by the time I get my statement in the mail or by email, I know that all of the transactions there are done and they're all complete. Eventual consistency is that mechanism of saying, I don't know what it is right now, but by the time it's done, I'll know that it's right. By comparison, ACID compliance, as soon as I'm done, I know that I'm completely done. So SQL, ACID compliance, consistent rows and columns, that really elegant SQL mechanism, SQL query language, that's really cool. On the upside, we have a strong schema with SQL. We can do table joins. It's a very optimized engine, very familiar and compatible syntax. On the downside, this mechanism is optimized for storage size. When we talk about third normal form, we do that so that we can store data smaller. And storage isn't really a concern anymore. We can store lots of things. So normalizing our data may not be a necessary thing to do now. Ultimately, these databases are usually not designed to scale horizontally. Most of these database engines were crafted in the days when one processor was sufficient. And so to make a SQL database go faster, I put more RAM and more hard disk in it. I make this processor one big beefy box. So there are mechanisms to scale them horizontally, but they're usually add-ons and decently fragile. Ultimately, you may hit that limit where vertically scaling becomes infinitely expensive and you just can't find a big enough box. One of the other downsides with SQL, it's often best with an ORM, and that's another layer of complexity because, SQL data is not objects. Okay, so some examples of SQL databases are here. And for the most part, a relational database is a good first choice. If you end up with a monolithic database, it's probably a SQL database. Next up, NoSQL. Now, I'm going to call it document databases because from now on, for the most part, they're all not SQL databases. They're not relational databases. But generally, when we say NoSQL, we think of these document databases. Now, these document databases will generally store JSON documents like the one here on the screen. Now, this JSON document is interesting. It has nested properties. It has different data types. I can do whatever I need to do to get my object into my store, and it will stay as an object. That's pretty cool. What's also really cool is different documents in my data store don't necessarily need to be the same type of document. I may have a few common fields, but I may also have fields that are different or older versions that I just don't bother migrating to the new schema. That's completely fine in a document database. Each document is on its own. Now, I'll create these collections of tables in NoSQL are generally called collections, but these collections will be kind of isolated things. So I can't really do joins across collections. Now, there are mechanisms to try and fake that, but for the most part, one of the principles of NoSQL is no joins. They're generally optimized for reads, and they're generally focused on eventual consistency. So pros and cons, we dug into some of these as we were looking at it. It's distributed usually by default. NoSQL is kind of a more modern mechanism. And so with databases of this type, I generally have lots of little boxes, commodity hardware. That's really cool. I have no schema, so I can have different documents with different fields in it, and that's totally fine. That's kind of also a con because if I have no schema, my application still has a schema. It still understands each record as kind of more or less this way. And so if I don't have a schema, I may have to build additional error handling logic in my application to be able to handle cases where a field that I expect to be a particular type isn't, or a field that I expect to exist doesn't. So it's a little bit of complexity in my application to compensate for not having a schema. They are denormalized, which means it's faster reads, but it also means that because it's denormalized, when I want to write, I may have to update many places. Now, I've specifically chosen that. I'm optimizing for reads, but that does mean that writes are a bit more complex. And we talked about no joins. I also don't have transactions in document databases because they are distributed. And I'm focusing on eventual consistency. So here's some examples of document databases. Document databases are great when I want to render the whole thing really fast. So for example, a news site. On a news site, I have the title of the story, I have the body of the story, I have the author's name, maybe the author's bio, I might have a list of related stories, I may have the first few comments for that story. I want all of that to pull based on one thing, so I'll have the slug for this news story, the URL, and I'll reach into my document database based on that URL, and I'll grab the entire JSON document, render that to the page really fast, and that's how I get my news site to behave quickly. Having to do joins across lots of tables to be able to do that, I really want my news story to render really fast so I can get lots of traffic. So that's when I might choose a document database. So next up, graph databases. Now, graph databases are really good at focusing not just on the data, but also on the relationship between data. So I have objects, nodes, and I also have relationships between nodes. What's really cool is I have this really sweet syntax where I can start to navigate those relationships here in the query. So not only do I have relationships, but I can store data associated with that relationship. We can think of friends of friends. So graph databases, how is that different from a SQL table with two foreign keys? Maybe I have this intermediate table, foreign key off to the first table and foreign key off to the second table. Yeah, that's how I could fake a database, graph database inside of a SQL database. But ultimately, the graph database is about these really elegant queries, this mechanism of being able to traverse those relationships really easily. By comparison, if I do this in a relational database, I'm probably doing a lot of self-joins to be able to do that. Okay, so join on myself and then join on myself again, and now I have friends of friends. It's just a little bit less efficient. So on the upside, graph databases are really optimized for fast joins across relationships. On the downside, because they're optimized for this, they're not optimized for, well, everything else. So I would choose a graph database specifically when I want that type of relationship experience. Here's an example of a graph database. It's best used for messaging apps and social networks and recommendation engines when I really want to focus on those relationships between things and put metadata in those relationships. If I have other use cases, then maybe a graph database isn't a great choice because I'm sacrificing some of those other pieces to make this graph database work. So next up, a KeyValue database. A KeyValue database is great for get by ID type of scenarios. I can think of a graph database as a table with two columns, one that is an ID and one that is a value that is, just stuff. Now it could be a JSON object serialized to text. It could be a big binary blob. It could be different between different records. When I read by ID, I get that blob and I can see all of the data. So a primary key and a binary blob. And so I'll go get by ID and I'll get all of the data out of that blob. So on the upside, these are really fast for get by ID queries. I can store different types of data in each record. So it's, pretty much schemaless. On the downsides, I can't really query by anything else. I'm really optimized for get by ID. Now, yeah, technically I can get by other things, but the way I do that is I basically get all the keys and I loop through each key, deserializing the value using whatever mechanism makes sense for that value. And then I use a different technique to query into that value to see if that value matches. So really not a very efficient mechanism to do that. If I need that get by something else, then I probably need a different table type. But KeyValue is great for cache in that mechanism where I need to go get by ID and I need to get all of the data associated with that ID. It's great for configuration data where I can have a particular key and the JSON settings associated with that configuration. each entry into my key value store doesn't need to be the same type of data. So I can store different types of configuration in my key value database based on the type of use case that I have. Here's some examples of key value databases, and Googling those will probably help you find others. Time series databases. Time series databases are great for identifying time windows. What's really interesting about relational databases is when I have a cell that is a match of a row and a column, I probably only have one value here. What's interesting with a time series database is once I have that row and column, I may have multiple things in that cell. I have all of the values that fall within that time window. So because I have multiple values, I can do really elegant things like show me the max of those, or the min of those, or the first, or the last, or the average, or the sum. I can do those types of things across these time windows that makes that really efficient. So here's kind of a SQL syntax over the top of a time series database where I have this really elegant mechanism of grouping by buckets of time. So time series, they're great for those windowing type of functions where I say, okay, so give me a day and give me all the values within a day, or an hour, or 5 minutes. Show me all of the values within that and normalize those values across a thing. So perhaps I want the mean values across that window. On the downside, I'm trading that windowing for, well, everything else. If I also have other needs of my database, I may choose to not have a time series database. But time series databases, here's some examples of time series databases. They're great when I have lots of event-based things. So maybe I have mobile devices sending analytics data, or maybe I have a whole bunch of sensors with their values and their times. Stock trades is another one, click streams. In each of these scenarios, I have a lot of data, and it all has a time component to it. So as I'm analyzing it, I probably want to analyze it within time buckets. And that's great for time series databases. Next up, text search databases. Now, text search databases are great for querying text. We can talk about a reverse index. When I'm looking at a text search database, my goal is, does this document contain this text? Or which pages of this document contain this text? That reverse index is really helpful there. I may choose to pair this with a natural language processing system so I can ask it regular questions and it can answer me, but it doesn't necessarily have to be that. The great example of like the Google search engine is a text search database, well, paired with a natural language processing system. So with text search databases, it's great for finding references in documents, but there's no relationships between documents, and it's really only best for text. Another thing that's really interesting here with text search databases is stop words. In English, a, of, the, an, a, these words don't usually have a whole lot of meaning in and of themselves. And so I may choose to mark these as stop words and drop them from the index. Well, that's interesting, but it's also very culture and language specific. And so if I'm storing data across many languages, I may have different stop words that apply to different languages and don't apply to other languages. Another place where we can get caught in stop words, let's have stop words associated with addresses. So we'll have the normal a and an and of and things like that, but we may also have av and road and st, things that don't have inherent meaning in and of themselves. Well, that's interesting, but what about when I have Avenue A? Well, I've dropped A and I've dropped av, and so now my address in my text search database is nothing. Stop words can really get us in trouble, both culturally and contextually. So we need to carefully identify the stop words. Inside the context of our application, we may also have domain-specific stop words that are interesting based on the use case of our application. So text search databases. Here's some examples below. The cool thing is that Elasticsearch will apply the schema ahead of time, and Splunk will actually apply the schema as we query, which is really interesting. So they're best used for finding keywords in documents or finding matching documents. But outside of that, it's not all that useful. I can't do joins. Object stores or blob stores. We might think of these as file systems if we squint real hard. The key is a path, and the value is a big binary blob. Now, the cool thing about object stores is that that big binary blob can be really big. So maybe this is the way I store database backups or store large image files. And then the key, that path, I'll put that in a different database, and I'll have that then as a foreign key off to a different data store. So I'll pull up my record, and it'll include a link off to that big video file, and then I'll grab that video file from the object store. On the upside, I can query by ID really easily, not that unlike key value stores. On the downside, I really can't query within the content very easily. The way that I would do a filter by something else is I would loop through all of the keys, deserializing the value, the object data. Maybe I'm un-gzipping the backup, and then go use a different search technique to go through each piece of data. That's intense. Now I've just paired two different database types together. Object stores are great when the data content is really large, but when the data content isn't really large, it's probably best to store this data somewhere else. So here's some examples. Amazon S3 is kind of the canonical example of a file system like file system blob store, but Azure Blob is also a really good choice. And that network share that you have, the SAN, could be a great object store. It's best for big things that need storing, but not great for random access within those things. You can't wear on it. You can't do foreign key relationships. Column stores. Column stores are really interesting. An adaptation of a relational database used mostly for analytics. The data is stored in columns instead of rows, and each column then has links off to other fields. So for example, here on the left, we have kind of that traditional SQL database or row store. And so in each row, all of the data associated with that row is more or less stored together. By contrast, in a column store on the right, we store each column together, and it may have links off to other pieces. So this is really interesting. So for example, well, what if I'm storing states or countries? Well, there's only a certain number of countries. And so I know that my value is going to be one of 200 some odd values. So I can probably compact this row, this column quite a bit. That's really cool. That allows me to store a whole lot more data, a whole lot more succinctly. Then when I want to get all of the things for a particular country, pardon me, I'll quickly seek to that spot in my column store index, and then I'll bulk read all of the things associated with that country. That's where column stores can be really efficient for those quick seeks and then bulk reads of all the related data. So on the upside, it's great for compression. It does faster seeks. On the downside, it doesn't do great at random reads and writes because, well, I have to seek to that spot and then I have to read. Column stores are great for bulk analytics, but they're not great for transactional data. Here's some examples of column store databases. We can think of these as OLAP or analytics databases, which can be really cool. So I get my data into the analytics database, and now I can query it really fast, and now my dashboard works really well. So we've talked about a lot of databases that may or may not be familiar to you. Let's dig into one that may be brand new. Before we go there, any questions so far? So let's dig in. NewSQL databases. We can think of NewSQL databases as relational databases that are distributed. And that's a really good mechanism for crafting a new type of database, because now we have a mechanism to be able to scale our databases with commodity hardware. We like scaling things in the document database world, and we like the relations in the SQL world. And so this becomes that best of both worlds. Here's an example of the MemSQL database where they have aggregator nodes, and those will receive user queries and break that query up into the pieces responsible for each leaf node that stores the data. So on the leaf nodes, each of the leaves store data in partitions. And so that leaf will pull out the data that it needs from each partition. And then the aggregator will aggregate those results back together, order them properly, and return the final result. NewSQL databases are great when you need to scale up your SQL database beyond where the normal SQL database can go. When you get to that limit where vertically scaling becomes too expensive or impossible. So NewSQL databases are great. They're cheaper to scale. On the downside, they do have more moving parts. We do have a new partition mechanism. And so we need to keep track of, well, what is our partition key? What is that mechanism that splits our data into pieces? And that might be a concept that we don't really understand yet until we get a good feel for our data, or we don't really get how to optimize that to store the data more efficiently. Simultaneously, when we do joins, well, what if part of my data is in one leaf node, one machine, and part of my data is in another one, and I need to join? There may be some network access to be able to put this data back together. Now that's the major new piece, is that network access to be able to do joins. But other than that, I can think of this as pretty much a standard SQL database. I have the same mechanisms of ACID compliance and the same SQL syntax. I just now have the ability to scale in really elegant ways. Here's some examples of new SQL databases that can do some interesting things. When would I use a new SQL database? I would use it when I outgrew my relational database, when I have too much data, or when I need more users, or I need faster response times. When I have that spinning wheel waiting for my data to load, that's the time to start looking into new SQL databases. If I've also optimized my queries sufficiently to be able to optimize based on indexes and other things. So hybrid databases. Well, I may need some features from this and some features from that. And that's where a lot of databases are no longer just purely that particular type, but they're kind of hybrid. They're a relational database, but they also have a JSON column that allows them to do NoSQL-like things. Or perhaps they're a relational database, but they also have time series windowing functions that allow them to do time series queries. If I wanted to do a key value store without a separate key value database, I'd build a table that has one primary key and one big blob value, and I have a key value database in the middle of my relational database. I may choose to have databases may have row stores and column stores in one database, and that works out really well as well. I see a lot of databases moving in this direction towards a hybrid database model, so that you're not making quite as big a trade-off when you need that additional functionality. If you do have a problem that is very specifically tuned to one of those problems, then by all means, dig into an exact perfect solution there. But if you have, well, mostly this and a little bit of that, then that's where hybrid databases can come in really handy. So here's that money shot. If you grab these slides from robrich.org, or if you fire up your screenshot, here's all of the database types, kind of a one-word description of that. and when you might choose this as the best database for your particular problem. One thing to note here is that relational databases, SQL databases, are probably a good default choice. If you don't know your data schema yet, or you're just diving into the problem, starting with a relational database is probably a good choice. If you do understand your problem really well, or your technology is more tuned to other things, then choosing the database specific to your type of problem may also be a perfect starting spot too. We looked at architectures. We looked at the monolithic database and the micro-dbs. We talked about how we can use bounded context with a monolithic database to make it start to pretend to be a distributed database. And then once we have enough automation in place to get the security and the backup features in place, then we can move that monolithic database to micro-databases without a whole lot of trauma, because those bounded contexts have already helped us identify which service needs to own which type of data. In particular, as we dug in here, we use the example of the customer. Who owns the customer? Well, we may need to create a new microservice that identifies only the bare minimum of customer data, the customer's primary key and the account number. And then each other microservice may choose to publish its data across a data stream using event sourcing, and other microservices may choose to consume that data stream if that data is applicable to them. Because we now have micro-databases, not all the databases need to be the same type. Here's another great screenshot to grab each of the types of databases and look through the types to see if your problem is best met by a different data storage strategy. Now, in the realm of micro-databases, each microservice may have more than one database. Maybe I need an object blob store because I'm storing large amounts of data, but I also need a relational mechanism over the top, or I need a NoSQL cache of content. So maybe I can now search through the cache and do wheres on non-primary key things. Once I find the unique ID that I need, now I can go into the object store and read that blob. Or I may need a search database, a text database that allows me to search through interesting things and find the documents. But I may need to store additional metadata about each document in a relational or a NoSQL database. Each of these databases has their perfect spot. And if you find a problem that is exactly matching to the strengths of that database, you can use a micro-database to solve that in really elegant ways. Here's another one to take a screenshot. My recommendations: ultimately, use a database as a service if you can. All of the cloud databases, cloud vendors have mechanisms to keep that database up and pretty much 100% of the time. And if you do need to restore data from backup, they'll do point-in-time restore for you. You don't need to manage all of that mechanism of how do I get to point-in-time restore? Where did those backups go? The cloud service will do that. That's definitely something you probably want to outsource. If you end up with more than one database server, use automation to be able to subscribe it to the backup and user authentication details. Default to a SQL database to get ACID compliance and the most compatible syntax. And use other database types if they exactly match your use case. Because you can have lots of little databases, then you may have a use case that is perfect for a time series or a graph database for a portion of the workload for your application specific to one microservice or a portion of that microservice. And then the other pieces can use a relational database. This has been a lot of fun. We haven't had a whole lot of interactivity because Hopin hasn't made it easy to ask questions. But what are your thoughts? What are your concerns? What are your questions? Good info. Thanks, John. This is really great stuff. Thanks, Sean. What database types have I left out? What different data stores have you used that don't fit into these buckets? Working on moving a single MySQL database over to multiple micro-databases. And this was a great introduction to different options. Very nice. That'll be fun as you split up your MySQL database into lots of little pieces. It'll be interesting to see which pieces gravitate towards other types of data stores. That would be fun. I think for most people, decentralizing data takes experimenting. This includes trying different types of databases. I completely agree. To that end, if you can get to that point where you can spin up lots of different types of databases, start to play with them, build non-critical applications with them, or little pieces of functionality with them, and start to experiment with them and get a feel for which data store works best for which use cases. You may be surprised because sometimes a data store really doesn't fit the problem that you've chosen for it. The cool thing with micro-databases, it's usually really easy to back out and use a different type of database instead. Pre-built Docker container databases make it really easy to play. You are correct, John. With most of these database types, you can find a Docker container that has that database in it. And at that point, Docker compose up and you've got your data store. Make sure you map your volume if you want this data to be durable, because I've done that a few times where I forget to map the volume. I do a whole lot of stuff. I bring the database down and yep, the data's gone. But Dockerizing databases really makes it really effective to play. At that point, you just have your volume that is how that database chooses to store the actual data. And the database engine itself is completely contained within the container. Ooh, good call. Other questions like price, support, etc., are quick in the architecture discussions. You are right. As you experiment with each of these databases, some of the characteristics that may be important to you is open source or price or support, and that may help you tailor within the category. So perhaps you need a NoSQL database that also has enterprise support, or perhaps you need a relational database that is free. Those are really good decisions. Good call. What common problems would I face moving micro parts of a system into a document database from a relational database over time? Good call. Probably the first thing that you're going to hit, Robert, is that doing joins in a document database is really computationally expensive. So as you move from a relational database into a document database, you'll want to very carefully denormalize your data. Now you're denormalizing it, which means whenever you do an update, you may need to write to multiple records. Because you don't have ACID compliant transactions, some writes may succeed and some may fail, getting you in a really weird spot. So keep track of that. Does it make sense to have an array of children, or does it make sense to have a different collection with those children as different records? Those are good experiments to start to play with as you look at a document database. I think one of the biggest things that starts to bite me with a document database is that eventual consistency. Eventual consistency, as long as it succeeds, is not bad. But eventual consistency that fails in the middle is really scary. On the upside, document databases scale horizontally much easier. And so you're much less dependent on the one big database server with a document database. That's where NewSQL can be really helpful, because if you migrate from SQL to NewSQL, you have that built-in horizontal scale. Banking uses eventual consistency. Yes, that is kind of funny. Of all the things that I want to be just perfect all along, money is a big one. But yeah, money is eventually consistent. That is kind of hilarious. Cosmos uses 5 levels of eventual consistency, and understanding the pros and cons of each may help in the decisions. Yes. Cosmos is primarily a document database, a NoSQL database. But one of the things that Cosmos does really well is global scale. So all of the pieces of the data will be available in all of the regions really quickly. You pay for that benefit, though. But yes, they have lots of eventual consistent to more transactional levels. And so picking the right one can be really, really cool there. I wish they'd use the Cosmos scaling engine with a SQL over the top. Now, I grant that they do have a SQL-ish kind of interface over the top of Cosmos's Mongo experience, but it's still not truly relational. But that global scale is really cool. Oh, 5 levels of consistency levels. Eventual is 1. Sorry about that. No worries. That was cool. I got that wrong as well. Well, this has been a lot of fun. If you find other questions in the coming days or weeks, or you're watching this on video, hit me up on Twitter at Rob_Rich, and you can grab these slides right now at robrich.org. Click on presentations, and you'll get straight here. Thanks for joining us. This was a lot of fun.